Hola amigos, ¿qué tal? Welcome back. We finally made it to the end of our introduction to applied linear algebra. This last sequence of videos is going to focus on something called the eigenvalue problem. I would say that we saved one of the most challenging and rich problems for the last one that we studied. This eigenvalue problem is going to show up all over the place. You'll see that in this video. Strictly speaking, when I say the eigenvalue problem, it makes it sound like it's a single problem, but that's not the case. The eigenvalue problem actually describes a whole collection of templates for different types of problems that arise in the wild. In linear algebraic theory, we usually categorize eigenvalue problems into three different types of problems. We're going to see all three of those in this short introduction. The first one is the least complex, and that's known as the standard eigenvalue problem. In the standard eigenvalue problem, we're given a square n by n matrix, and then we're searching for scalars lambda paired with vectors x, such that when I multiply a times the vector x, I get a scalar multiple of the vector x out. This scalar is known as an eigenvalue, or a standard eigenvalue, and then this vector is the associated eigenvector for eigenvalue lambda. That's the Greek letter lambda. A second and more advanced eigenvalue problem that shows up is something called the generalized eigenvalue problem. Starts with the same left-hand side as the standard eigenvalue problem. Have a given modeling matrix A. I'm looking for a vector x such that lambda times b times x is equal to a times x. The reason that we call this thing the general eigenvalue problem and this the standard eigenvalue problem is one, this is the standard from which all other eigenvalue problems arise. And then two, if we look at how this standard eigenvalue problem works out, we see that we could actually put an identity matrix in between the scalar lambda and the vector x, because I know the identity matrix times x is just x itself. The moment that we do that, we drop an n by n identity matrix in between those. We might ask ourselves, hey, what if instead of the identity matrix, that was just any general n by n matrix? Well, that is the general eigenvalue problem. Replace the identity matrix with a general square matrix and still maintain the same relationship that a times x is equal to lambda times a matrix times x. In the standard eigenvalue problem, that matrix is the identity. In the general eigenvalue problem, it's a general matrix. In the development of these theories, once we've mastered the standard eigenvalue problem and general eigenvalue problem, usually we would go on to master something called the quadratic eigenvalue problem. And in the quadratic eigenvalue problem, we start with modeling matrices M, B, and K. Each of those is square and shows up in some real-world modeling context. And then we're looking for eigenvalue eigenvector pairs in the form lambda and x, such that lambda squared m times x plus lambda b times x plus kx equals 0. Claim the transformation from the general eigenvalue to the quadratic eigenvalue problem includes some advanced mathematical theory. And in fact, in our introduction, we're not even going to touch these later two problems. I did want to mention these more general problems because the work we do to study the standard eigenvalue problem sets the foundation for these more advanced techniques. When solving each of these problem types that are grouped together and known as eigenvalue problems, we're going to focus on two different categories of theory. For now, let's filter all of our work through the standard eigenvalue problem, since this is an introduction and the focus of this introduction is going to be on the most foundational of the three problems. The good news for us is, as we work to solve standard eigenvalue problems, we can dip into large volumes of theory that have been created over the last 350 years. I'm going to encourage you to think about that theory as having two categories. The first category is what I would call an algebraic approach to solve each of those problems. Each of those problems, strictly stated, are in algebraic terms, so we can use theorems and pen and paper analysis to work through each of the challenges that arise in those problems. The other approach that is very, very powerful is something called a numerical approach to solving these problems, which is, instead of doing our work with pen and paper analysis and quoting theorems, can we store our modeling matrices on computers and then use algorithms, software on those computers to generate eigenvalue and eigenvector information associated with those matrices. At this point in human history, we've been solving eigenvalue problems numerically for about 70 years. 1950s was really the first foray into this after the ENIAC computer. Many of the best algorithms in the world that implement solvers to find eigenvalue and eigenvector information are based on theoretic and algebraic results that give insights into these problems. Because this is an introductory course, my main goal is to help set the foundation for your future study and hopefully help you cultivate some interest in learning more about this theory. With that in mind, let's focus in on the standard eigenvalue problem and talk where it arises in the world around us. Here's a verbal description of the standard eigenvalue problem. Given a square matrix A that has n rows and n columns, we want to find all scalars lambda and associated n by 1 vectors x such that when I multiply A times the unknown and desired eigenvector x, I get the scalar lambda multiplied by x. Let me call your attention to a few different features of this algebraic statement. First, when we say given, we mean we spend days, weeks, months, or years generating that matrix from some valuable modeling problem. And then the goal is to find these two separate quantities, a scalar and a vector, that when paired together satisfy the condition that multiplying the modeling matrix by the vector gives a scalar multiple of that vector out. Some fun intuition that I like to think about is if I imagined A to be an audio system and I imagine X to be the vector of my vocal input to that audio system, lambda could be the volume that the audio system puts out. And in an amplifier, what I hope is when I put my voice into a microphone, the audio system amplifies my voice out. In other words, when I put that vector into the larger system, I get a scalar multiple of that vector out. The system only scales the vector. It doesn't fundamentally change the vector underneath. Now I'm going to make a claim. When working with students, I generally say that my students are geniuses. They have so much valuable lived experiences. And one of the jobs that I have is to actually show them they already know the mathematics that we study. They just haven't recognized it in a formal setting like we would in school. So we're going to play this game, Have You Ever? Have you ever heard a car rattle when you turned the music up really, really high? So really high volume and you hear the so the bass is going and you hear that rattling sound. Let's look at a different situation. Have you ever felt the steering wheel of your car shake when you put the brakes on and slow down? That happens all the time in my Honda Odyssey. The thing shakes as I'm slowing down. Have you ever tuned a string instrument like a guitar or violin? How about purposely jumped up and down or back and forth on a footbridge that was hanging between 2 points and felt the thing kind of sway back and forth in a predictable motion? If you answered yes to any of these have you ever questions, then my claim is you've actually experienced phenomenon in the real world that can be mathematized as an eigenvalue problem. Another way to say that is if you were willing to spend a few years of your life and you were super excited about doing this, you could actually turn each of these problems into an eigenvalue problem using formal mathematical technology. The bad news is that each of these applications, if I were to actually mathematize those to state the standard eigenvalue problem, I would probably need at least one separate bachelor's degree for each application and maybe even a master's degree to do the entire modeling problem start to finish by myself. In other words, in an introductory course where the goal is to introduce ideas, we have this trade-off between showing students why this is powerful and placing reasonable expectations on students to be able to study an introduction that sets the foundations without overwhelming the student or putting too much burden on their shoulders. However, I want to avoid the trap of not mentioning the future applications and just going right into the theory. With this in mind, I want to touch on briefly some of the much larger application areas that eigenvalues show up in as a way to motivate your curiosity. One of the questions I always ask myself is, why should I care? How can I use this in my future? And why does it matter to me? Let's see if we can help you get answers to those types of questions by focusing on other people's answers to those types of questions. The first field in which eigenvalue problems are ubiquitous, I would call mechanical vibrations analysis. Another way to say this is it's the study of things that move back and forth or shake. In other words, the study of physical objects that vibrate. Vibrations analysis. For engineering students who are thinking about any design of suspension systems in any type of moving vehicle, another word for this idea of vibrations analysis is called structural dynamics. Here's a book by Craig and Cordelia called The Fundamentals of Structural Dynamics. And what you see on the front here is this apparatus where you have a real car. In the background, there's a computer model of that car. And the axles of the car are connected to a suspension system that is connected to a data acquisition system that allows the engineers that design this to test the response of the designed system against different stimulus on the road. Another way to say this is, suppose I have like a mass on top of some springs. There's also some fluid inside the springs, like a dampener. And on the bottom of that system, we've got this wheel, and the mass and the wheel go over these bumps called speed bumps or potholes or whatever. And the question is, how does the displacement of that wheel show up over time? So if I hit the thing up and the springs compress, what's that look like? Do you see stuff moving back and forth? Yep, that thing's going to go up and down. And the moment that it goes up and down, we're thinking eigenvalue problems. That's a vibration problem. Now, the funny thing about this problem is it has this analog that's going to show up all over the place. And in fact, we're going to study this quite deeply because it's the foundations upon which this problem rests. That analog is called a mass spring system. So in this case, you got to think like, okay, the mass is sitting on top of springs, and then I'm literally like changing the way that the mass is related to the spring. And the question is, how does the displacement happen? Well, that's what's happening over here. That vibration problem is a lowercase example. It's not as complex as the suspension system example. Another situation in which this arises is the brake system in any vehicles. That's exactly the phenomenon that I was talking about. When you push the brake of your car and you feel that rattle, that's a vibration. When you see vibrations, think to yourself, oh my God, there's probably an eigenvalue problem underneath this. Another example of where eigenvalues show up in mechanical vibrations analysis is analyzing the motion of buildings during earthquakes. I do want to give a call out that all of the diagrams that I get either came from this book by Craig and Cordelia or this book on mechanical vibrations by S. Rao. Don't run and go get these books immediately. If you go take upper division classes in these theories, I actually get a lot of information out of these books, but the diagrams that you see here come from both of those books. Remember, the claim is that vibrations problems, physical objects that shake back and forth under different phenomenon, those give rise to eigenvalue problems. Check this out. If I have a 4-story building where each story has steel beams, and then this large mass, which is called the floor itself, and the beams are called the structure, and then I shake the bottom of that thing, what is the corresponding motion of that building? Claim that problem is at least the 4th year of an undergraduate and more like a master's or PhD problem. There have been multiple generations of PhD and postdoctoral researchers who have studied the theory behind this problem. And then there's entire engineering firms that hire very well-educated people to do this type of analysis when designing buildings. But if we're thinking about introductions, we can map this larger problem down to a much simpler problem, which is if we have this mass attached to 2 springs, hey, mass and springs, are you recognizing a pattern? Mass and springs. And then that mass has this little joint connected to another mass, and then we shake the mass on the bottom, so we literally like perturb it back and forth, aka an earthquake happens. What happens to the mass sitting up here given the stiffness of that joint? We can use observation and intuition that we build about this simplified problem to analyze the much more complex problem, which is how do buildings shake under earthquakes. If we wanted to up the ante even more, we could also talk about the motion of bridges in wind. This is a super complex problem and requires a ton of education to even understand the statement of the problem. I want to give a shout out to engineers that have to take a course called statics. So on the front of statics books, you'll often see like these bridges. And in fact, later on, there's something known as a truss system, TRUSS. Here are a bunch of different truss systems corresponding to designs of bridges and cranes. In statics, you look at the response of a particular system under a static non-moving force. In other words, this is all algebraic analysis dedicated to systems with many, many different components. Generally, just as we started our mathematical analysis with algebra and then went into calculus, statics sets the foundation for a more complex theory, which is called dynamics. So in the analysis of the motion of bridges, you would take a statics classes to figure out what truss systems is, a dynamics class to figure out how things move and how they respond to time varying forces. And then you would take a number of specialized courses in the materials and construction of civil structures. That's what civil engineers do. I did want to give a shout out and just show, in every dynamics book and even statics book, we'll always have these conversations about vibrations and time responses. And in fact, here you see the suspension system of a car, and there's a nice diagram associated with that. And it is really, really funny that almost every single time, the places where all these conversations start is spring mass systems. Just in case my aeronautic and aerospace engineering friends were feeling left out, don't trip. Guess what? These vibrations analysis problems show up in the dynamics of motion of the wings of planes in flight. In a rudimentary introductory analysis, we can think about a plane as having a mass and then two long wings attached to that. That's the fuselage and the wing from a front view. But then when I think about this, those things could be point masses. We could model those as point masses at the end of the wing, and then the mass in the middle, and then springs connecting each of those long rods to the actual mass, so that as the thing goes up and down, you see this kind of up and down motion, this vibration of the wings. And the question that we ask ourselves is, well, how does the different forces that the wings experience relate to the up and down motion? And have I designed my system in such a way that the wings aren't going to fall off when in flight? Once we have intuition about that introductory problem, we can actually make it much more interesting by discretizing a larger wing. So there's the mass, and then instead of thinking about a single mass on the outside, we can think about like 12 separate masses. We can kind of lump together the different elements along the wing and discretize those masses. And then the question is, as we move the plane up and down, what are the different forces experienced, and how does the actual motion of the wing relate to those forces? Electrical and computer engineers, were you feeling left out? Don't trip. Eigenvalues show up in electrical circuit analysis and design. And specifically, there's something called resonance in circuits. This is part of resistors, capacitors, and inductors. Linear circuit analysis, that sets the foundation for computer-aided design in circuits and many of the other techniques that engineers use when designing circuits. Eigenvalues show up as a fundamental tool in that analysis. For computer and signal processing engineers, this also shows up in computer image compression algorithms. Eigenvalues can be used to compress large amounts of data into smaller amounts of data. In fact, recent fields known as machine learning and data analysis, this is all the rage in many of the technical fields. Many techniques in those fields are based on this concept of principal component analysis. Principal component analysis is at its heart an eigenvalue algorithm. And the hits just keep on coming. There's something called Google's PageRank algorithm. This is the fundamental technology that Google used to get off the ground. There's a great book on this by authors Langeville and Mayer called Google's PageRank and Beyond, The Science of Search Engine. It goes very deep into the foundations of Google's technology. And I just wanted to show you that in the computation of Google's PageRank vector, they solve this eigenvector problem, which they state like this. This is a constrained minimization problem. Don't worry about that. That's called Rayleigh quotient. That's beyond the context of an introductory course. But the point of the matter is, without eigenvectors and eigenvalues, Google would not exist in the form that it currently does. Similarly, Netflix old prediction algorithms of ratings. You ever been watching a Netflix show and they're like, oh, we 98% predict that you're going to like this movie, and then you click on it because they're like telling you what you like and what you don't like? Their old algorithm was based on prediction capacity using eigenvalue theory. Moreover, when we're thinking about the structures behind how to turn real-world modeling problems into eigenvalue problems, many of the ideas that show up in our mathematical modeling of mechanical vibrations actually set the foundation for a much larger field called finite element analysis. And just to show you how powerful this is, many of Boeing's planes starting in the 1980s, The engineers that designed those planes, the teams of engineers, actually used finite element analysis to design the entire structures of the plane prior to getting the first model built. There's this famous workflow problem where we go from the mathematical model of the plane, the mathematical analysis that arises using finite element methods, to building a small version of the plane. I think that's called a sting. So here, this version is actually like the size, smaller than the size of a human. It's connected to all these sensors, and then there's these wires that come down, and the plane will actually, this small version will fly under similar conditions that it would see in the real world. So they have like these wind tunnels, and they expose it to all these forces. And the question is, using the information they collect from these data and the mathematical analysis that they have in finite element method, can they iterate enough to produce a plane that works well and that they can certify that the $1 billion of investment that it takes to build will not be a waste? Finite element methods also show up in the analysis of wind turbines. Could you imagine what vibrations happen when you're having a large set of blades move around in the wind? You'd have vibrations of the actual blades, you'd have vibration of the foundation, and you see what's happening here is we're discretizing the entire metal structure into these small points and then edges. The points are masses, the edges are like springs, and then the question is, as we expose this thing to a bunch of different forces, what happens? That brings us into a bunch of applications having to do with health analysis. So there's a finite element analysis of cuts on a human hand and the corresponding sutures that come into that. Movement of the human heart and how blood flows in and out, the shearing and compression forces experienced in a car in accidents, weather models for pressure and precipitation, models involving rockets and rocket science. So here we have a bunch of masses and a single beam. Here we start putting the shell outside and then we compose them together, which means we can do analysis on each individual component, fit them together and do analysis like that. Models of the frame of a school bus or any bus that moves people round and round. The list just keeps on going. And what I want to show you is underneath all these crazy models are mass spring systems. Literally in the same form that we've been studying in this class, where you have a matrix K, a right-hand side vector F, and then a vector of displacement U along each point mass. Is your jaw on the floor yet? Let me just go ahead and close that mouth for a second. The eigenvalue problem sets the foundation for so many problems in applied mathematics and engineering that this problem is famous for math heads. The goal of an introduction is not to get into the advanced theory. That's the purpose of a bachelor's, master's, and PhD program. Instead, what we do is we set a foundation upon which the advanced theory can be built. So, in order to start setting that foundation, I want you to go back and look at the list of applications that we just covered, and I want to show you two themes that show up. Number one, the first theme is that many of those problems are continuous problems. What I mean is they exist in time and space. The way that I would say that as a mathematician is those problems, the analysis of brake systems, the analysis of train motion or rockets or planes or bridges or buildings, those involve math that are built on calculus. In other words, the equations that govern that have continuous functions in the equation. That is beyond the scope of algebra. That's not working with equations that involve scalar valued variables or algebraic equations. That's working with differential equations, equations that involve functions and derivatives. Thinking back to our own time studying algebra and calculus, remember that calculus has a lot more going on because time is difficult. It's so much easier to analyze stuff that is static than stuff that changes, which implies, is there a way that we can use our knowledge of algebra to say something meaningful in calculus? That's exactly what eigenvalues do. They turn continuous problems into discrete problems. They turn calculus problems into algebra problems. The second theme that shows up is that many of those problems involve systems with a large number of dimensions. Now, large is relative. If I've only done mathematical analysis on a system with one dimension, and then I go to 2 dimensions, that's much, much larger. But what you'll see is as we increase the complexity of our model, more and more components are included in the models that we use to get closer and closer to real life. From that context, eigenvalue problems and eigenvalue theory is often used to reduce large number of dimensions to a much smaller set of key dimensions that still replicate the fundamental behavior of our larger data using a model with much smaller dimension. Because this video is not meant to be all inclusive, and because I know that many of my viewers are super curious and want to know more, I want to show you how you can find out more from other YouTube content creators. If you go to my website, appliedlinearalgebra.com, go over to blog, scroll down to Math 2B Linear Algebra, and then scroll all the way down to lesson 27. That's my first eigenvalue lesson. If you see the eigenvalue extras playlist, go ahead and click on that. This playlist is a collection of videos that I found over the last few years where different content creators are spending a lot of their time putting together what I would call relatively strong stories about eigenvalues in the real world. I'm not going to test on this in my class, but I do want to give you access to those resources so that if your curious mind seeks answers to questions like, wait, I want to learn more about that idea, these are some places that you can find answers to that outside of my learning resources. I hope that list of applications sparked some curiosity and got you thinking about your own academic interests and how you might leverage this technology in your future. For us in this introduction, my goal is not to get advanced. My goal is to set a very solid foundation. So when we study the standard eigenvalue problem, which is given a modeling matrix that is n by n square, find a lambda scalar and a vector x that when paired together satisfy a times x equal lambda times x. We're going to motivate this problem by studying what I like to call a keystone application that gives rise to an authentic eigenvalue problem that you're going to study using your eyes, hands, and actually feel in our course. Now, you might not understand what I mean by a keystone application. Let me talk about that. I like to think about keystone applications like I think about the keystone in a Roman arch. If you've never heard of that idea, go ahead and search the term keystone on Google or DuckDuckGo, and then go to images and you'll see these beautiful images of these arches made of stone, and at the very, very top there's this keystone. And in fact, there's a beautiful Wikipedia page on keystones in architecture that talks about the keystone as this center stone. So if you didn't have that keystone in the actual arch, the entire thing would fall down because the stones themselves are cut in such a way that all of the stones kind of line up, and then when you put this keystone in, the arch supports itself. It won't fall over. And in that way, the keystone allow this to be a gateway, allow this arch to stand up and let stuff pass through it. Similarly, when I'm coaching young students, I look for keystone applications that will hold up our theory and can be used as central components for future gateway studies. And so what I mean by that is, once you have this foundation, you can pass through a bunch of new information and the arch that you built in your introduction won't fall down. You have a very, very solid understanding that's based on these critical ideas. So from that standpoint, in our introduction, I'm going to actually give you a keystone problem, which is a version of that spring mass problem central to so many of the ideas that we just covered. Not only that, but I'm actually going to guide you through the process of mathematizing our problem and then using fundamental eigenvalue theory to solve that problem and give useful information about the dynamics underneath. With that in mind, my objectives for our eigenvalue theory are the following. Number one, I'm going to help you build your own eigenvalue problems from a phenomenon that you observe in your real world. Number two, I'm going to help you learn theory to solve this problem using introductory techniques and computer tools. Number three, I want to actively help you plan for and describe more advanced eigenvalue problems that you might want to study in your future academic and career pursuits. And the hope is that this introduction makes that future study much easier. At the end of my work with students, I always ask them to grade me on my effectiveness in accomplishing these goals. I would challenge you to do the same thing. In the next video, let's hop into the keystone application and get a sense of how that application works as a way to motivate eigenvalue theory. I'll see you there.